We're nearing the end of Unit 7. This is 7.6. I can recognize functions and compare graphs. So compare right here. Now the warm-up here, it says, how do you find the domain by looking at a graph? So if we want to find the domain by looking at a graph, here's what we do. We squish all of the points, squish it onto the, remember the domain are the x's, so we squish it onto the x-axis. So by the same token, if we've got a graph and we want to find the range, then we would squish it onto the y-axis. So I'm just going to put some quotes here, squish it onto the y-axis. Okay. Now, which of the following have we studied so far this year? Piecewise, quadratic, exponential, linear, reciprocal, and power graphs, power functions. So the three that we've talked a little bit about piecewise. We haven't talked about quadratic. You've dealt with quadratics last year, but we haven't done any of that this year. Didn't even do any graphing last year. We did some exponential this year. We definitely did linear. We've done a whole bunch of that. We haven't seen any reciprocal graphs or functions, and we haven't seen any power functions yet. So down here on this paragraph, it says different functions behave differently, and they make different shapes when we graph them. So that's the big idea here. When we graph a function, it makes a shape, and different functions are going to make different shapes. They also have different domains and ranges. All right, so that's why this question came up in the warm-up. We're going to look at some functions today that look really familiar and then some that will look really unfamiliar, haven't seen these shapes before. Here's our goal. Our goal is to identify some key features so we can compare the shapes. All right. And once we compare those shapes, we've got some basic features and stuff. We're going to be able to look at kind of the overall behaviors and stuff like that and maybe answer a few questions. Now, please don't forget that x and y-intercepts are a really important part of any graph. If it's got an x-intercept, we want to grab each one of those if there's more than one. And remember, it can only have one y-intercept, so that's an important point. If it's got a y-intercept, we want to make sure we have that. You might want to think about why it can only have one y-intercept if it's a function. All right, let's slide down here and let's take a look at these three. The instructions help us out quite a bit here. It says use a graphing calculator to sketch each function. We want to label at least 3 points on each one. So we're going to grab a calculator. So I'm going to pull this up and I'm going to shrink this down right here. And let's see. Let's go through. Let's put y equals, let's do x. So there's the variable key right here. And we're going to raise that to the third. And again, I always like to kind of hop down and hop on another line so we can see, yep, does that look exactly like what we want? So again, standard graph here, let's graph it in the standard window. You'll notice that we've got this set up from -9 right here over to +9. So -10 to 10 is going to be okay. So let's go ahead and hit zoom 6. Standard window right there. Haven't seen a shape like that before. Remember, if you're trying to figure out, some important key features on a graph or what some of the function values are or where those values are, we can always hit the trace button. So you'll notice that this does cross at the origin. So I'm going to put a dot right there at the origin. Okay. And then let's go over here just a little bit. Okay. The really ugly function values here. Okay, now let's get a point on here. So while we're in trace, if you just hit the number 1, it's going to change the x to number 1, and then instead of going to pixel values, it will actually calculate what that is if we hit enter. So 1, 1 would be where it is. Okay, so we're going to have a point right there. If you want to check another one, we could try and go over to 2, but you'll notice the ugly numbers right there. So I'm going to hit a 2, and I'm going to hit enter. Now that should kind of make sense because if we plug in a 2, we would cube that. 2 times 2 is 4, times another 2 is 8. So we've got this point right here. Okay. Now going the other direction, it looks like it's pretty similar, but let's come down here. Let's see if we can get some function values down there. Again, more ugly numbers down there. So I'm going to type in a -1. So we've got at least one negative value. When we plug in a -1, we get -1. And that should make sense because when we cube a negative, there's 3 negatives, so it turns out to be negative. So we're going to get a graph that looks something like this. Goes like that, like this. We'll put some arrows on each end, and it did say label at least 3 points on each one. So I'm going to graph -1, -1. Remember, the origin was on there, so that's 0, 0, and that point right there was 1, 1. Okay, so we've got 3 points labeled on that one. I'm going to come back here. Now, I'm going to turn this function off. I'm going to go ahead and leave it there. Because we might need it later on. And I'm going to type in 3 over 2 raised to the second. So this is an exponential. We do 3 divided by 2, and then we're going to raise that to the x. So again, notice the big difference here. The base here is the variable. On this one, the variable is the exponent. We'll hop down here, make sure that that looks right. Looks pretty good. And let's go ahead and hit graph and see what we've got. Now, we've seen exponentials before, so that's no surprise right there. We should know that what the y-intercept is on this one. So let's go ahead and hit trace. 0, 1, it goes through that point right there. That's exactly what we'd expect. Now remember, if we plug in a -1, we should get the reciprocal of the base. The reciprocal of the base would be 2/3. So let's just check and see what happens when we plug in a -1. We get 0.6 repeated, so it is 2/3 right there. So I'm going to put a 2/3 about right there. Okay, and then this next one, if we go over here, let's try and get on 1. And we run into that whole problem with decimals because it's jumping from pixel to pixel. So I'm going to type in a 1. We're going to hit enter, and we get 1.5. So we're about right there. Okay, and I want to get a little better value. So I'm going to plug in a 2, and we get 2.25. So 2.25 is right there. And if we wanted to go a little bit further, let's say we plugged in a 5. So we plug in a 5, and we get 7.59. So that's not a whole lot better, but 7.59, so we'd be about right there. So that's enough that we could graph this. So I'm going to go ahead and run in like this. Again, I'm right-handed, so I tend to graph better going this way, although if we were to do it properly, probably runs along here, hits those points, and then goes up. Remember, we have an asymptote over here of y equals 0, and then we've got that value right here, this value right here, and this value right here. So we've got 1, 3/2, that was 1.5, 0, 1, and then we have -1, whatever the reciprocal was, so that's 2/3. So again, notice what we've got here. We've got the -1, the 0, and the 1. The 1 goes with the 0. If we plug in a 1, we get exactly what the base is, and if we plug in a -1, we get a reciprocal of what the base is. Okay, we should know what this one looks like. That one's a pretty easy graph. That one's linear, so I'm going to come back here. I'm going to turn this one off, so we'll hop on top of the equal sign, hit enter, and then we're going to plug in 3x plus 4. So 3x plus 4. Now, before we have this graph, let's just take our best guess here. This one should cross at 4 on the y-axis, so it should be right here. And then it should have a slope of 3/1. Rise 3 and run 1. Other way would be down 3 and back 1. So we should get something that looks like this. Now, we've got the 3 points on here, but remember, we want to know what the the x-intercept is also, because that's an important point. We got this x and y-intercept was the same thing. This one did not cross the x-axis, but it did cross the y. So we're going to say 0, 4. This one right here is 1, let's see, 5, 6, 7, 1, 7. And then we'll try and find that other one. So let's go ahead and hit graph. Looks pretty good. Let's hit trace. We've got that value right here. Let's hit 1, make sure we got a 7. We did. And then it would be cool if we could just say y is equal to 0, but let's come down here and let's see if we can get as close as we can. So what I'd like you to notice is right here at -2.7 or 1.27, the value is positive, so that means it's above the x-axis. And then over here at -1.48, it's below the x-axis. So somewhere in between there, it's got to have an x-intercept. It's got to have a y equal to 0. So that does look pretty good because we're between -1.48 and -1.27. Looks pretty good on our graph right here. Little trick that we need to be aware of, if we want to find an x-intercept, we want to find where the function value is equal to 0. So I'm going to put a little 0 right here, and then just like normal, we have a math button that will allow us to calculate some math stuff. But if we're on a graph, calculate has some cool things on it. So we're going to hit calculate, and is there anything right there that helps us figure out, we want to figure out where this crosses the x-axis. We want to figure out where the y is equal to 0. Well, if you'll notice right here, it says 0. So I'm going to go ahead and hit that, and it says left bound. So left bound says, give me a little window where you want me to find it. So we're going to make sure we're to the left of where we think it crosses the x-axis. Puts a little arrow up on the top. It says right bound. Put it on the right side of where we think it crosses the x-axis. And then it says take a guess. So let's get that number as small as we can, so about right there. And then it's going to work for just a second, and it says -1.333. Now that's a third right here, so that's -1 1/3. So that is -4/3. Now, something cool about this, what would happen if we just set this equal to 0? We want to know when this function is equal to 0 because that would mean it's on the x-axis. If you move this to the other side, that's negative 4 equals 3x. And if you divide by 3, we get x equals negative 4/3. And there's our negative 4/3 right there. So tons of information right there. But let's come down here and take a look. It says state the domain and range of each function up above. So let's do domain and let's do range. So the domain for this one is you can squish this onto the x-axis. You can get any number you want. You can plug in anything there because we don't have any domain issues. So this is going to be negative infinity to infinity. Same thing for the range. We get all these negative numbers and a bunch of positive numbers out. So this is negative infinity to infinity. We've done an exponential before. So the domain on this one, just like the other ones, negative infinity to infinity. We do not get any negative values out and we don't get a 0. So this is going to be from 0 to infinity. If we were to squish this onto the y-axis, we don't get any values down here. And then that linear function, just like most linear functions, we don't have any domain issues. You can plug in anything you want, and then we get out anything you want, okay, from negative infinity to infinity. It says look at the shape of the graph and determine if it's linear, exponential, or something unfamiliar. Well, let's look at this one right here. There's no way it can be linear because it's not a line, and we're really only familiar with piecewise and exponential functions other than that. So this one is unfamiliar. Unfamiliar. This one right here is exponential. Exponential, we've seen that shape a whole bunch. And of course, this last one is linear. Now, it says graph all three functions on the calculator at the same time. Which one grows the fastest as x approaches infinity? So as x approaches out infinity, that would be out on the right end. Make that look like a G. So out on the right end. And then it says explain how you can tell. Now, if we come back over here, I'm going to hit the y equals button, and I'm going to turn every one of these back on. So this was why I left these on here, because I knew we were going to be doing this. So I've got all of those on. I'm going to hop down here. We've got x to the third. We've got 3/2 raised to the x. And then we've got 3x plus 4. So I'm going to hit zoom 6. We're going to graph this in the standard window, and we'll take a look at this. Okay, so the first one, this x to the third, it grows really quickly. I mean, look how steep that is. The line comes along like this. It's pretty steep. And then we've got this exponential that's kind of going up, but not very much. Okay, but nothing interesting is going on here, and we're not interested in out in the left end. We're interested in the right end because we want to know as x goes to positive infinity. So here's what we're going to do. We're going to hit window, and we're going to change these values a little bit. We're not interested in what happens on the negative side, so we're going to go from 0 to 10, and then we'll leave the scale like that. We're not interested in any negative values because all of these go up from left to right. Their end behavior is they tend toward positive infinity. So we're going to do 0 here, and I'm going to go up to 100. Now, if you don't change the scale on this, that's fine. Let me show you what happens here. Let's just hit graph really quickly. Okay, so this was x to the third, and this was the linear one, and this was the exponential one. Okay, now we've got kind of a big black line over here. Let me show you how we can take care of that. If we come down here and we change the scale, by putting the scale at 10, what we're going to do is we're going to put from 0 to 100, we're going to put a tick mark every 10. So that means there's only going to be 10 tick marks. So go ahead and hit graph. That looks a little better over there. Now, it looks like this x to the third, that one grows really fast because it's really steep. The linear one's kind of trailing off. It's like the exponential one's kind of in second place. But let's change this just a little bit. Let's go a little bit larger. And this is one of the cool things about a calculator, how much investigating that you can do and how much regraphing you can do really quickly just by changing a couple of buttons. Now, I'm going to go up to 1,000, and then we're going to go by 100. And let's see what happens on this one. Okay, there's our x cubed, okay, and there's our linear one. Okay, so here's our exponential. Now you'll notice that they're starting to look quite a bit similar, but let's change this. Okay, so hopefully everybody agrees that, that the linear one is out of the running. It's not growing very fast, but these function values, I'm going to go ahead and hit trace. That's up at 1,000, and this is up at 1,000. Okay, so it's at the very top there. So we're going to come back here. We're going to go to window, and let's get a little extreme. Let's go to 50. Oops. 50, and let's put a tick mark every 5, and then let's go to, should we say like 10,000? 10,000, and let's come down here and we'll put a tick mark every 1,000, and let's hit graph. Okay, so here we start to see some kind of surprising behavior. Look, you can barely see that linear one right there, but look what's happening now. That exponential is getting really, really steep. So we're going to come back here and we're going to do this one more time and we're going to see what happens. Let's go to 100. All right, and then we're going to do a tick mark every 10 just to keep those axes from looking really ugly. And then we've got, let's go to, that was 10,000. Let's go to 100,000. All right, there's 100,000, and we'll do a tick mark every 10,000. Again, the tick marks aren't a big deal. You could change that every time. It just kind of helps make things look nice. So let's go ahead and hit graph. Okay, now this is kind of cool. Take a look at this. This was that x to the third. We call this a cubic function right here. Okay, you can't even see the linear one because we're going up to 100,000. And if I hit trace, so we're at 125, 50, 125. Watch what happens if I hop on the exponential. Okay, holy cow, look at how big that is. So 3 halves raised to the x. If I plug in a 50, we get, let's see, that's 637 million, okay? So in the end, now it took a little bit of investigating, in the end, that exponential one won out. It was growing the fastest. So let's come back over here and let's answer this question here where it says, which one's growing the fastest? Okay, so out near the right end. So graph all 3 functions on the calculator at the same time. We did that. Which one grows the fastest as x goes to infinity? Well, that's the exponential. So that was that g of x? I'm pretty sure that was g of x. So g of x equals 3 halves to the x grows the fastest. Okay, grows the fastest as x goes to positive infinity. And we could say a couple different things here. It is the steepest. It's the steepest by the time we get really far out there. Has the biggest function values. And anything that you can think of that kind of points to the same idea. Now, I'm actually going to go back here and I'm going to grab this. I'm going to grab a picture of this. And we're going to take this, we're going to copy it, and I'm going to paste this right here. So we'll go ahead and paste this. And this is our picture of what goes on here. So I'm going to make this just a little bit bigger. This is kind of our evidence. And you'll notice that what we have here is when we're on 50, we've got that 637 million. That's that one that's growing really, really quickly. I think the other one was just like 125,000 or something like that. So big difference there. The exponential grows the fastest. All right. All we're doing today is just kind of practicing throwing things in the calculator, recognizing different features and properties and behaviors of functions, exploring a little bit on the calculator, really good skills to have. Go ahead and fill out the self-assessment right there and then get started on the assignment.